that will be for accessing the materials, the follow-up, and any assignments. And we shall give you access to that. So for now, register in the system, in this Zoom platform. We know you are here. Then on a case-by-case basis, as we conclude today's session, we shall be able to make sure that all your concerns are covered. Thank you.
Okay, thank you, Doctor, for that clarification. Just know we are not segregating you in any way. All this material is freely available for everyone. So don't worry, you'll be given access to the platform. As I'll probably tell you that 60 people registered for the training, but we're only seeing 152. In other words, you who is here, you're actually more serious than probably somebody who registered and they're not available for the training. So you'll be given the privilege. So that shouldn't worry you. All right, so let's dive into the major part of the training. So one, we shall look at I've already mentioned a number of these, so I'm not going to repeat them. But quickly, we shall look at definitions of GIS and remote sensing, the different components within the GIS and remote sensing, data models, coordinate system, map projection, and what datums are, look at map scale features and map design, dive into spatial databases, analysis, and geoprocessing tools. And then, of course, the most important thing is to dive further and look at GIS application in different areas, but have a demo on a case study in natural resource management. We shall also, in remote sensing aspect, look at what electromagnetic spectrum is and how important it is in remote sensing and Earth observation, and go further in how the energy from the sun and sensors interact with matter or Earth objects in space and on land. We shall also do a quick theoretical understanding of what Earth observation data acquisition processes are, how to store and do the processing. Of course, in this processing, we'll be looking at the image processing as well as how to analyze these images. The last part will be how the remote sensing is applied in natural resource management and food security. So you'll be interacting with a number of these materials in this area. Today, we're going to be focusing on what the definition of GIS and their components are, spatial data models, coordinate system, map projections, and the datums. And then we finalize with map scale features and map design. So GIS stands for acronym of what? That is Geographical Information System. Don't think of GIS as something so magical. It is simply a computer-based system which aids you to collect, maintain, store, analyze, generate or visualize outputs, as well as it goes further to enable you distribute data and information. Now, this data that we're talking about must be spatial in nature. And in details, we're going to look at that, what spatial data really means at a later stage. But what we are saying here is that there are two things. There is data and information. So data is basically something that is raw, and information is something that you processed and generated an output from the data. So it's a tool that helps one to make and use spatial information. And key to all definition of GIS is a where and a what. So this is what makes the GIS as a computer-based system unique, in that it has very key words that must come along with it. There is a where and a what. Where is something, and what is something. So a GIS quantifies location of a place by recording their coordinates, numbers that describe the position of these features on the Earth. So what we shall look at details what coordinates really mean. But basically these are numbers on Earth. So when you're talking about GIS, you're already thinking about coordinates. So coordinates and GIS are very much friendly to each other, or they go along with each other. A GIS may be used to record the height of trees. It can be used to record the population of your country, but also it can be used to record the depth of a lake, ocean, as well as any other defining characteristics of each spatial features. So just like to mention, GIS is just a tool that you use for doing a number of activities. And these are just some examples. If you want to measure the height of the tree, you'll ask yourself, what can I use? Can I be tall enough to reach the top of the tree or at the canopy level? Maybe not. For some trees, you can. For some, you may not. So how can you do that? You could use a tape measure to measure the height of the tree, but that will be possible if you're doing maybe for 10 trees or 100 trees. What if you have 1,000,000 trees? How can you measure the height of the trees at a go? So GIS will help you do that. Look at the population of the country. If you ask yourself, how long does it take you to count the number of people in the country? GIS can enable you perform that. Maybe you could take over 4 years to count the whole number of people in your country, but with GIS, it might take you maybe a week or a month to do that. The depth of the lake, just imagine if you want to measure the depth of the lake, that means you have to dive into the lake or the ocean up to down and measure its height or the depth. But then how possible is that to a layman person who even doesn't know how to swim, or we even don't have the gadgets to do that? So in our ministries, in our workplaces, at this point, we can be able to measure the depth of an ocean. Personally, I've just been around the Indian Ocean once, but I've never gone inside, maybe with a boat or something like that in the middle of an ocean. But with GIS, I can be able to measure the depth of that ocean even when I'm not there. So all these aspects are things that we can utilize the tool, which is the GIS, to do. Now, why do we need GIS? Why are you really part of this course? So it's because day to day, we are faced with a number of questions. If you're invited for a workshop or a meeting, one of the things they will give you a descriptive location of a place. Of course, now technology has improved that people can share with you a WhatsApp pin or a Google pin, a number of ways people describe that. But all in all, what it's doing is trying to share with you information. And you have a question, you're asking yourself, okay, they have invited me for this ceremony, for this party, or they have invited me for this workshop, for this meeting, but where is it located? That could be a very simple example, but give yourself a question. For example, you are doing research and you have a question of where things are located, how are they distributed, what is associated with them, how does it interact with other things in your study area, and how has it changed over time? So those are some of the questions that we are faced with when we're doing either research or we are just doing an investigative study of any kind. or we're just implementing a project. Let's say you work for an NGO and you have a project that you need to implement. These are some of the things that you have to write in your concept note or in your terms of reference or in your proposal that you're making to do the research. So for example, you'll ask yourself, and the first question would be a geographical location-based question. Here is where you ask, where is it? Why is it there? Okay. Why is this there? And how much of it here or there? So how much of that thing that you're trying to study is, and where is it? Another question could be, so when you've known where something is, how much of it is in that particular place, you also want to go ahead and ask yourself, but then, is this distributed locally or it is distributed globally? You can also ask yourself further, is it spatially clustered or is it dispersed? So those are some of the questions that you'll be having in any activity that you're trying to do. Let it be research in this case. Another important question will be the geographic association. So what do we mean by the geographic association? Here is where you are asking question, what else is near that object or that thing that you're studying? Okay, let's say you probably studying maybe an urban center. What else is near those urban centers? Are there water bodies? Are there some rivers? Are there some market areas near those urban centers? Then you're going to also ask yourself, what else occurs with it? Because what is very important is that when you're doing some bit of research or you're doing study or implementing a project, these other things will influence the success of a project or of the research that you're doing. So you should ask yourself what else occur with it, and GIS will help you answer that question, probably much better than if you go and handle it by the questionnaires. Then you can also go ahead and ask yourself, what is absent in its present? Because all these things will influence the success or the failure of that initiative or project. The other question is also on geographic interaction. Geographic interaction. So what is this about? So is it linked to something else? So if you've known what is associated with that initiative or that object that you're studying, or maybe the project that you're implementing, you'll also ask yourself, what about the geographic interaction? Is this project linked to something else? If your project is, let's say, you're trying to improve agricultural output, you're introducing maybe new seeds to the communities. It's maybe because you want to increase agricultural productivity. But is that the only problem that is affecting that community? Maybe the output of agriculture in that area is small simply because they're not receiving enough rainfall. So the linkages between the low productivity of agriculture could be due to poor rainfall distribution in that area. So you could maybe think about, okay, maybe I introduce aspects of irrigation. But as you will see, rainfall is associated with the geography of an area. So you can then use GIS to be able to understand some of those aspects. If you want to introduce irrigation, you'll ask yourself, okay, where am I going to get the water? So with GIS, and remote sensing, you'll be able to tell what is near, what else is linked or near those particular areas. And then you'll ask yourself, what is the nature of association? In this case, low rainfall results into poor yields. So that's more like a direct relationship. Or less rainfall in this case results into poor yield. So that's a direct relationship. But there are some interactions that are opposite. Okay. When people get more money, there is less crime. That is just an hypothesis, an assumption that I'm making. When people have more money, there's less crime. So that is indirect relationship. If people are poor, there's more crime. Okay. So what is the nature of this association and how much interaction occurs between the location, if the location is what you're trying to look at in terms of the geographic interaction? The last key aspect or the last key questions that GIS can help us answer is on geographic change. So has it always been there? So for example, if you're studying, let's say, pollution, okay? So you'll ask yourself, maybe pollution due to sewage or pollution due to the flooding and all those things, different hazards. If you're looking at flooding, for example, as an hazard, you'll ask yourself, how has it always been there? So has this particular area been experiencing flooding? Okay. And how has it changed over time and space? So do we frequently receive floodings in that particular area? Or let's say earthquakes or mudslides and all those things that you can be able to study. Has it changed over time and space? And what causes its diffusion and contraction? Or in case if it is a landslide, what is causing the landslide to increase or decrease over time? So those are some of the questions that GIS as a tool can be able to help you answer if you get to know how to use it. Okay, components. So let's look at the components of a GIS. So GIS is composed of what we call a hardware. Like I just mentioned, the GIS is a tool. So it's composed, but this tool is a system. And that's why it's called a GIS or Geographic Information System. So it's composed of different components. And one of the components is the hardware. And then we have a software. Then we have the data component. We have the human component and a set of organizational protocols. So these organization protocols that we're talking about is maybe a procedure. It may be a model. It might be maybe a code of some kind that you can use to allow the software, which is installed in the hardware, manipulate the data by you. Okay, so you must have a procedure that is used by the software, which has been installed in the hardware, or let's say a laptop in this case. And this software will use the data or manipulate the data, and the human is you who is doing the work. So you'll see that GIS as a system is interlinked, and these are the basic components that it has. So these components must be well integrated for effective use of the GIS and the development. And the development and integration of these components is an interactive, ongoing process. So it's a back and forth. Let's say you go to the field, you use a GPS or your phone to collect the data. You come back with your phone, you use a computer to enter this data. And when you're going to enter this data, you might have to use a software. In this case, it can be an Excel or it could be a QGIS. Okay, so when you enter this data, you manipulate this data using a certain protocol and then be able to generate the product that you have. So this cloud of words is just trying to highlight the different components that GIS has. In the center, of course, we have the geographic information system, which is in short form is GIS, and it has the software. There is a technology aspect of it. There's analyze, store data. There's aspect of information. There's something called spatial with it, location, cartography, and presence. There's also aspect of accuracy. Don't forget, the data that you must utilize in the GIS must be accurate enough. Of course, we have the mapping that we keep hearing. Everybody keeps saying, I want to develop a map. So GIS doesn't only stop in mapping, it goes further to do modeling and managing of the spatial data. Of course, before that is done, the core of GIS is that the data must be in a digital format, not just any data. Of course, GIS data can be in the form of a printed map, but to utilize it better is you must first convert it into a digital format. So this cloud of words is just trying to highlight the different components of the GIS. This figure is trying to dive deeper and also highlight, break down the different, from the 5 components that we saw, what is entail or what is part of that. So in the hardware, if you've heard of satellites or you've interacted with one, I wish to touch the Ugandan launch satellite someday. But basically, these are part of the hardwares of the GIS component. We have the GPS, of course. We have the networks, the computers, the servers that serve you data. We have also printers and plotters, mobile phones and sensors. So we'll dive more in sensors when we shall be looking at remote sensing. The software has the different version of them. We have the desktop software that we are more familiar with, and probably a little bit on mobile application software, so GIS. But don't forget there are web applications and also web services that are part of the softwares of GIS components. The procedure, like I mentioned, or the protocol in this case, include things like modeling, analysis, data collection, and representation, as well as presentation of the data. Within the data framework, we shall look at more in detail shortly. There are aspects of what a vector data is, a raster data, the 3-dimension models data, and also the different online resources that are part of the components of the GIS data. The you who is here today in this training and attending this training, these are the researchers. We have researchers here. We have developers here. I know of one developer in this platform. There are specialists. So you're specialists in different aspects in your ministries or in your workplaces. And then we have people who are just interested in making maps. So if your part is you want to be somebody to develop maps, and these maps go a long way, not only just the normal study area maps, there are quite a number of cartographical maps that are used in surveys and all that, the card designs and all that. So those are all under the cartographers. This list is not limited. It's very wide. If you look at only researchers alone, there are a number of researchers that are out there, and they are researching in different fields. Others are hydrologists, like one has mentioned today here in this platform, that their interest is to understand how to use GIS in hydrology. Others are foresters, others are meteorologists, others are surveyors. There are a number of researchers and specialists or specialized fields represented in this training today. So all of you are catered for in this big balloon here of what GIS is. Now, to go further, looking at the different things we see each and every day in terms of the GIS components, we have the digital typewriter. That used to be a GIS hardware some years ago, and it's still used for some parts of the world as the data entry platform. We also have the digitizers. The digitizers, I know you may have not used digitizers for so long or much. I don't know if could be very few of us here would have used the digitizer, but we used to have what we call the table digitizers. Now we have the advanced digitizers, which basically you digitize things from your computer. If you've ever digitized a road from Google Earth application, for example, you've performed what the digitization is all about. Okay. We also have the normal typing, which whenever you go to the field, you collect data and then you come back and type it in your computer to basically enter it. So those are the typing of data. So you'll realize that these are the input gadgets that we use for entering the GIS data. Next, we have the management components that we use in GIS. For example, the laptop you have right now, and maybe a workstation. Workstation is just a desktop computer, for example. Of course, these days we even have laptop workstations. So, I mean, technology has grown so big. So those are all things that you can use to manage the data. So when you come with data from the field, then you enter it during the input here. You want to manipulate it. You want to generate maybe the sums, the means, and all those things. Also, you want to just summarize your data, maybe do the cleanup and all that. So all that you're doing is basically managing your data. Then after that, you've generated an information from your data. You can go ahead and generate an output. I don't know if some people have seen plotters. I've ever seen one. So you can use plotters. Plotters are basically huge printers. They are large printers that you can use for printing your maps, but also normal printers can be used. Don't forget that your output is not necessarily printed out. It can also be in a digital form. So right here, you'll be able to use a digital data, put it in a CD, or you can even share it in a flash, or you can just upload it on your Google Drive and share with your friends or your workmates and so forth. So this is just trying to depict the different components in a pictorial way of what is in the GIS. Some of these terminologies like CPU might be very advanced for some of us, but basically what is in your computer or your the box, let me call it the box of your desktop computer, is the CPU. So you realize that every time you connect your desk, you connect it to the monitor, you connect it to the printer, you connect it to a scanner, you connect your keyboard and the mouse into your box, as well as you have a platform or section where you can insert your flash, as well as your CD. there used to be a time where when we had what we call the floppy disks. I don't know if some people use the floppy disk, but it was a breakthrough in terms of technology revolution during that particular time. On our right, you'll be able to see that these are still the components of the GIS, but represented in a different way. Okay, what is this trying to explain? That you need to have, if you're going to work with the geographical information system, you must have coordinates, and these coordinates should be text input devices. So the coordinates, you use the text input devices to enter them into the big picture of the GIS. Now, also the storage process, or what you use for storing the data and manipulating it, should have rapid access, and the storage must be a mass storage. Archival storage is also very important. When we generate our data, we need to archive it so that we can be able to access it even years after. Of course, the networks have already talked about that. The digital medias are like the flash, or for example, your floppy disk, for those who still use floppy disks, or you can have a CD. It could be a DVD, CD, all that are under the digital media outputs and so forth. So these are just the further explanation of what the GIS components includes. Juliet, you're going to help me monitor my time, and when the time for the break comes through, we can be able to have a short break and then continue. Okay, we have looked at the hardware components mostly, but now here, let's also look at the software components. This might be so abstract to you for some people, but for some people here, they could have seen this once in a while somewhere, or have even used it. You could have used it consciously or unconsciously. So in terms of the software family, we have the extensions or the libraries that are used in GIS. We also have the web map servers. We have the GIS web clients, like your browser, like for example, your Google Chrome or Mozilla, or some people use Microsoft Edge. Those are all your web clients that the GIS web clients that you can use for accessing and generating maps. But in the back end, there is something that is serving you that GIS data, and these are called servers. So the servers are smart enough to be able to store or provide you with the GIS data that has location information attached to it. We have, of course, the mobile GIS. These days, people can do a lot of GIS analysis, data collection, and so forth using their mobile phones, as well as, of course, the old technology, which is still standing and beautiful, the desktop GIS. Of course, when you're using this desktop GIS, there must be what we call the database. So a database is the one that stores the data. If you've ever been in a circle, or you've ever been in a group, I'll probably call it a group as well, there's always a treasurer. So the treasurer is the one that keeps the money. So just like in the GIS, this database is the treasurer. It's the one that stores the data. It keeps the data, and whenever you need it, you go there and say, no, can you loan me maybe some $100,000? I don't know, there are some circles that have a lot of money, maybe, or you just want $100, or you want just I don't know in Mauritius what currency they use. Uganda, we use shillings. So you can ask for maybe 10,000 shillings from your treasurer. In this case, you're also asking for data from the database of the GIS. Now, if you are keeping this data in your computer, then you can just access it directly from the desktop GIS. But if it is sitting somewhere in someone's computer, then you will need a server. So the server, the GIS server, is the one that will serve you the data from someone's computer sitting somewhere. Okay, so a server is a computer also, but it has a unique software which is called a software server. So it's the one that helps the computer work. So a computer or a hardware is just something that connects to power. Okay, it powers, it connects to electricity in this case, and then, but it cannot be functional unless there is a software installed in it. And the software plus the hardware makes GIS to come alive. So some of the functions that you commonly, or you'll be commonly using your GIS software to do are here. One, the most important is data entry, the most tedious, okay? It's data entry, where you do manual coordinate capture, you capture the attributes. Attributes are characteristics of an object. Let's say you're studying a building, or you're trying to assess or do anything about the building. One, you're going to capture the coordinates of that building. But two, you need to capture the attribute information, which are the characteristics of the building. And then you can also do a digital capture. So for example, you can use a GPS, or you can just use your mobile phone to digitally capture the location of that. And then you can, in other than data entry, you can do data import. Another key aspects that you can use a GIS software to do is editing. So editing is just directly editing, where you have information that you've already entered in your computer, but maybe they have errors, or it's not well represented, or you want to change or add something or remove something from it. So this is where you use the GIS software to edit your data. So for example, you can do a manual point, line, and area feature editing. You can do a manual attribute editing, or you can automate error detection and edit them out. The other key part is also on data management. So data management. Ali, I'm going to get back to you. Let me just finish the slide, and then you'll be free to ask your question. So on data management is where you can do a copy, a subset, or a merge of the data. You can also do versioning. We shall talk more on some of these terms in details as we move. Data re-registration and projection, summarizing your data, or you want to just reduce the records that you have. It might be too large and your computer cannot handle. You want to compress and index your data. So when your data is so large, you need to index it. Indexing is basically trying to tell the computer that every time I'm accessing this data, you use this information so that you can quickly locate where this data is, but also open it. Of course, the other functions that we are going to look at in details is analysis. You can run spatial queries, attribute queries, do an interpolation, do connectivity analysis, proximity and adjacency. You can run a buffering. You can perform a terrain analysis, boundary dissolve, spatial data overlays, moving window and map algebra analysis. All these analysis can be performed using the GIS software. And we are going to look at some of them or most of them in this process. Outputs looks at mapping, and where you design a map first and then you export it as a layout. You can also do a hard copy map printing. So for example, you have your maps that you've already designed that generated a layout, you can print it. And also you can decide to share a soft copy. In this case, we are calling it a digital graphic production. You can export in different formats, as well as look at the metadata outputs. So metadata is data about data. It's something that describes you. If, for example, you walk into a building, you'll find that maybe an officer or the security personnel will ask you for your ID. Your ID in this case is the metadata. It's something that is describing who you are, your name, where you come from, your age, and so forth. Okay, so this is all something that you can perform using the GIS. Ali, kindly give me, you had your hands up. And turn off your mic and then ask the question. Okay, so now we are going to perform a simple exercise. And in this exercise, we are going to do it, but also shall have a 5 minutes break after the exercise. So that's when we come back from the exercise, we can be able to discuss what we will have done in the exercise. So the exercise is about mental mapping, or it's about a mental map. So what are the mental maps? So these are maps of our environment that are stored in our brain. Mental maps also reflect the amount and the extent of the geographical knowledge and spatial awareness that we possess. Now, I'm going to ask all of us to obtain a pen and a clear sheet of paper. And then next, what you'll do is to draw a sketch map that shows how you daily move, travel, or drive from your residence, or where you sleep or stay, to your workplace or your education institution or your university. So just get a piece of paper and pen, and then you're going to sketch a map that shows how you move. It could be daily or something like that, from your home to where you work or where you're studying from. Now the tips are here. This map or the sketch that you should have should include the roads, the junctions in case there are, the roundabouts. It should also include the buildings that might be your home itself, the school, and also other physical objects that you meet when you're traveling from your home or your house to your workplace or university. The other tip is also that within your sketch, indicate in case there are something like a supermarket or a shopping mall, a restaurant, a church, or a mosque that you can maybe go through or pass along your way to your workplace from your home. Okay, I hope you're ready for the exercise. I hope you're ready for the exercise. So this exercise, yes, Fithi?
Yes, please. Sorry for the delay due to the internet connection. We are from Eritrean.
Okay, so if you've understood the question of the exercise, kindly go ahead and do that sketch map. You're going to do that sketch map not from here, but you're going to pick a piece of paper and a pen and sketch that map from where you are. The exercise is going to be for 5 minutes. So after 5 minutes, then we go for a break for another 5 minutes. Then when we return from the 5 minutes, we start sharing what we have sketched in our mental map. So Juliet, you'll help me keep the time. I don't know what time it is now. Let me see. 11?
It's 11.
Okay, it's 11. So we'll get back at 11:12. We should be able to get back at 11:12 and discuss what we have sketched in our map. Okay. At 11:12.
Why don't you
Hear me?
make it 11:15?
Okay, 11:15. Doctor
So that
advises.
they can grab a cup of coffee.
Okay.
Ethiopian coffee, Ugandan coffee, Madagascar coffee.
Okay, doctor. Thank you for that tip.
Yes.
All right. So at 11:15, we shall return with our sketch of the mental map that shows how we move from our home to our university or workplace. Yes, Peter.
Yes, good morning, Mr. Thomas, and thank you for this presentation. I wrote a question in the chat. I don't know that you saw it, but I was wondering where artificial intelligence and machine learning lies in the components of GIS. That was my simple question.
Okay, so Doctor, do you want to go first? Okay.
You can actually go.
All right. So artificial, this is to our participants, this is a very advanced question that Peter is asking. But basically artificial intelligence and machine learning, these days, it mostly comes into when you are doing the classification of an image. Now, machine learning, you remember if you've ever used any classifier in during the classification, let it be random forest classification, let it be you're just using support vector machine. So those are classifiers. The classifier in this case is a machine learning. So basically what I'm trying to explain is that when you're doing a classification, there is a point whereby you train the classifier. So then the computer, which is the machine, learns your training data. So it is learning what you've submitted as your training data. You're telling it that this is a tree, this is a forest, this is a wetland, this is blah, blah, blah. Okay. So what it's trying to do is that it's learning the machine, which is your computer or your software, is learning what you've supplied it. But now artificial intelligence is whereby let's say you want to detect very unique, let's say in the forest, and you want to differentiate between different tree species. Now the artificial intelligence come in here to segregate the differences between the different species of trees in the forest. And how does that work? So based on the artificial intelligence platform or technique, it will be able to tell in terms of the spectral reflecting signatures that is being shown on the trees that have been taken or captured by the image of the satellite. So it's going to go in and learn, first of all, do the machine learning part, and then segregate the differences between the different species in that forest. So all you're doing is you're doing an artificial intelligence. So an artificial intelligence also go further by trying to generate what you probably have not supplied the machine. So for example, if you're doing unsupervised classification, what you're doing is you're telling the machine to decide on the classes that it's supposed to have. So that's already an artificial intelligence. But this is just a simple example that I'm giving to explain the differences or how machine learning and artificial intelligence is being used in the GIS and remote sensing platforms. Thank you. Let's go for a break. Yes, Doctor. Please.
Maybe what we can do, since the time for the break is running, we can add on something as we start off with the discussion.
Okay.
On the mental map, since the time is running.
Okay. Thank you. All right.
Yeah, thanks.
Thomas?
Yes, Maria.
Can you ask Juliana at least to send again the link for joining WhatsApp group, or she can add the number which people are sending via chatting inbox?
Did the people register?
I don't know if it's for registration, but what she said it's for WhatsApp, what? So I sent the number till now, I didn't see, yes.
All right. She's listening, so I'm sure she's already taking action and adding them to the group. For some people, they sent wrong numbers, so that's why we are having challenges adding them in the group. But today is the first day, so I'm very sure by tomorrow there'll be a lot that will be sorted out. Ahmed, can you keep your question up to when we come back from the break? Thank you.
Yes, we shall have a session for some questions after the break, such that people can be able to follow up, but also for those who are having registration issues, Juliet has a backlog because the numbers are coming in and she's processing them quite fast. But I think as we move on, things will be better. Thank you.
Yeah. All right.
Let's go for the break, please.
Okay.
That means the break will go up to 11:20.
Okay, sir.
11:20, please. Okay,
all right.
Thanks.
Ahorita, Bismillah.
So welcome back, ladies and gentlemen. So now we are going to share, look at our mental map sketches. I'll just stop sharing, and what we can quickly do, maybe I give people maybe 1 or 2 minutes to prepare. You're going to flash your sketch on the camera of your, so make sure you turn on your video, not your mic, just only the video, and then flash, just display, give us a look of what is in your mental map. So let me give people just a few minutes to flash their to show us what they have sketched. So go ahead and just put what you've sketched on your camera. Simply what I mean is just do like this, something like this, so that I want to take a picture of what we have sketched. Hello. Kindly turn your camera on and then flash on the screen your sketch, something like this.
Please check on
Yes,
mine.
Paul. Okay, I see Samuel. Samuel, that's good. Ladies and gentlemen, can we just put on screen what we have sketched? I just want to take a picture of it.
Yes, I'm sharing mine now too. From Paul.
Okay. Yeah, I see Mugati. I see for Mugati. I see for Samuel. I see also for Joel. So just splash it on the screen. Guys, I can't see yours. I see for Ahmed, Abdallah. Next page. Is there anyone else who has put theirs?
Yes, Samantha, I'm displaying mine.
Okay, I can't see it though. Let me see.
Yeah. This is my
Page
map.
number 6, page number 7. Okay. So, hello. Very few people are showing theirs. What's going on?
My name is
Mine
Joel.
is also there.
Okay, John, I see yours. I see
Even mine is there.
Paul.
No, my
Uh-huh.
donation. Mine is here.
Where? My next
Oh,
page, I
yeah.
don't
Thomas.
see.
Hello. Thomas.
Yes,
Hello.
I can hear you.
I think mine.
Jamie.
Okay.
Mine is also there.
Agos, I don't see yours, but I see your voice.
What about man?
Okay.
Okay.
We are from Eritreans. We are team of
I
Eritreans.
see for Winfred,
Have you seen mine?
Wambua. Yeah, Ali, I can see yours. I can see for
Yes.
Peter Hongo.
Can you
Awesome.
Thomas?
Yeah, I'm capturing yours. Capturing them. Just okay.
Good morning.
Hello.
Good morning. Good morning, Thomas. Can you check on mine?
Yes, I am taking the pictures. Okay.
But now ours now you're not taking.
I am in the third page. Fourth,
I'm on the
sixth
first
page.
page.
Can you see my Thomas?
I could have taken it already.
Hello?
So we turn off the videos.
Yes. Yeah. Forward, I can see yours too. I've taken the picture. So it's because people are so many, kindly, if you can, just take it with a phone and then send it or capture it. I don't know, in any way possible. But also in the classroom, you're going to just upload what you've shared, what you've sketched. Later, I'm going to show you how to access the classroom and how you can be able to do that. Okay, so I'm going to give an opportunity to two ladies and two gentlemen to share what they have sketched. So I'm going to first lower all our hands, then I get to know who has raised their hand to share. Just tell us.
Thank you, Karen.
What you've kindly lower your hands so that are these new people who have raised their hand? Jen?
Yes.
Okay, Jen, can you flash what you've drawn on the screen and then explain to us what you are trying to draw?
I don't know. Can you see it?
No, I can't see
Hey,
it.
now where do I put it?
Jen, yeah, Jen, I can see it now.
Can you see that?
Okay, yeah, I can see it.
Yeah.
Okay, so Jen, what were you trying
Jen,
to?
I'm Jen. I'm the District Natural Resources Officer, Kavare, and I'm a PhD student at Mbara University, Science of Technology. And
Okay,
now I'm flashing where I work, where I stay, and where I work. I stay within the town, Kavare town, and driving to my workplace takes me about 5 minutes. And I live here. There is a stretch of about 500 meters.
Yeah.
And I joined the road that slopes from the main road, Mbarara Kisoro Highway, and it goes to Kavare NTC. When I joined that road, I move about still 500 meters. I joined the main road of Kisoro Mbarara Highway. Then slightly on my right, I branch off and take on my right, and I move up to Kavare
district local government. But
Okay,
on the
Jen.
right there, yeah, I think you can see the physical features I've put, the shops, the
Yeah.
saloons, and then the forest after.
Okay, so Jen, I'm going to ask you a quick question.
Yes,
For the
please.
roads, how did you, did you draw them as a line or as, how did you draw the roads?
The roads I drew as roads and lines and junctions. Yeah.
And then the shops and the buildings?
They are lines like you can see, but they are junctions joining those roads.
So for the buildings, you didn't draw anything, you just put the names.
The buildings, I put X's. The buildings are X's because most of them are shops and the residential houses. So they are
Okay.
X's. Where you,
Okay.
Then where you see the forest bit of trees, that's where the forestry is.
Perfect. All right, thank you so much, Jen.
Thank you
Next,
so
I'm
much.
going to go to Ahmed. Thank you so much, Jen. Ahmed. Abdallah. Ahmed Abdallah, yes. Okay, first show us what you've drawn.
Scotch map.
Yeah. Ahmed, go ahead.
Hello.
Yes. Go ahead, please.
Yes, right now, this is my.
It's him. Ahmed.
Yes.
So for the roads,
Yeah,
what did you draw as roads? What did you indicate? What is in your sketch in your sketch? How did you sketch the roads? Ahmed, please.
Yes,
How
I'm
did you
here.
sketch the roads?
Yes, are you here? This is a sketch map. Yes. I'm living here. This is in the Blue Nile in Sudan here, from home to workplace. So this is I'm living here in this area. Then I'll go through this road, and then here the water, drinking water corporations in this side, and then I return left and go to Earth, and then here you can find the station of the fuel, and then here the police stations in this area, and then this Blue Nile Parliament, and then I can reach to my place or my workplace here in the welfare and the social development here in the Blue Nile region.
Okay, Abdallah, can you respond to these questions I'm going to ask you?
Yeah, okay.
So for the roads, what did you draw as the roads?
Yeah. Did you?
No, I can see it, but I want you to just tell us.
Okay, I drove the road by the big lines here, the small roads. Yeah.
And then the buildings.
Yeah, and then I make the point of the stations and the institute and the workplace, and then I just draw the way I go from my home to my workplace.
Okay, so I see you've drawn some rectangles. What are those rectangles? The squares
here
and the rectangles.
Yeah, rectangles, it refer to the fuel stations here.
Okay. And then the squares?
And the squares here, the police office station.
Ah, okay, okay. Thank you.
Yes.
Thank you,
Thank
Abdullah.
you so much.
Thank you so much.
Yeah, okay. Okay.
Okay.
Bye-bye.
So I'll go to another lady. Rashid. Rashid. I think Rashida came before Mercy. So can we go with Rashida? Rashida Kabite Nasuna.
Good morning, everyone.
Good morning.
Hope you are getting me. This is my sketch. Are you seeing it?
Very well.
Okay. So that is it is having a boundary and a title on top, showing that a sketch map of a sketch map showing my route from my home, which is in Kansanga, and to office is Kampala Road. So
yes,
the roads are demarcated by the columns, and where you see round circles, those are the junctions, and the triangular things, they are shopping malls. There is an embassy, Shell. So that is basically what I've drawn. Now,
so what did you indicate as roads?
Roads, those columns, they are the roads.
The lines, those lines I'm saying, like columns.
Yes.
Okay. And what is in round?
Those are junctions on the road. Yes.
Okay. All right. Thank you so much, Rashida, for that. Salam alaikum. All right, so let's go to the last gentleman. I think I'm going to pick Joel, Paul Joel. I think you came earlier.
The one who came earlier was Kato.
Was who?
Kato Humphrey. I don't know if he's still there.
Okay, Kato. No, okay, let's just balance now. Kato is also from Uganda, so let's get from Paul Joel just to balance the countries a bit. Thank you.
Okay.
Yes, Joel, like we can see your sketch.
Okay, my name is Paul Joel from Nigeria, master student from University of Jos, Nigeria, environmental geologist. I sketched, okay, from here, my hand is pointing at my home, my house. So from here, I go through not a major road, but just, it's a road, it's a third road. From here is a third road, but from here, just a part. So I walked through this part and then I came to this place. Coming here, there's a church here that is by my right, by my left, and then going up a little bit, there's the mosque. And then from there, I reach the major road. So from my major road, I go down towards, I take a tricycle from here, and then to head to my school. I'm trying to go to my school, the University of Jos. So from here, I reach a roundabout, which is at this point. This road continue going this way, so I turn this way. Going to school, there's a market here. The major market here is a vegetables market. They deal on perishables. So from that market, the journey still continues till I get to my school, my university.
Oh, perfect.
So I just noted my university with that building. That is it.
So Joel, why did you decide to use squares and those things for the buildings as well as the lines for the roads?
I was trying to differentiate between the major road and the minor road, and then for the buildings, I Universities have mega buildings. They have gigantic buildings compared to the church, the mosques, and then my small house. So I felt I should use a bigger building for the university, and it has it's a story buildings. They have story buildings. So that is why I made it in such a manner. And also there's a secondary school around here while going towards my school too. It also has a big structure, so but not as big as the university structures. So I also denoted it with the square. And then the marketplace, I felt it has small kiosks and shops. So I made it small. So I just made it a small rectangular and rectangle shape to denote the shops within the markets.
Perfect. Thank you so much, Paul. All right. So thank you all for sharing your sketches. And for those who didn't share, don't worry, we have the platform, we have the classroom platform that we are going to share our sketches. This is just part of the assignments that we shall be looking through to mark as a continuous assessment for everything you're doing. So keep it, you're going to upload your sketch onto your classroom page, and then you'll be able to, we shall be able to see it and receive it. So I'm just going to project to you someone's mental map. Let's say this was my mental map, okay? So the questions that you should be asking yourself, look at your mental map and ask yourself, what did you choose to draw on your map? So some people drew a church, school, buildings, roads, kiosks. Some people drew markets, of course, different objects. We drew them on the road. And the simple reason is because we were imagining how we were moving from our home to our school or to the university or to our workplace. So we were imagining different components that we meet along the road. But also what was important is that things that are like a road, which is linear, we were showing them using sort of a line or maybe a column for that matter, because two lines then makes maybe something like a column. And then for the buildings, we were drawing them using squares, maybe giving them certain shapes. So those certain shapes, when somebody looks at them quickly can tell that, hey, this is a church, this is a mosque, this is a school. They can tell the difference between what they are trying to draw in the map. So another question is, how did you draw objects on the map? So those are things I have explained. What about streets, restaurants, malls, museums, or any other point of interest? So we see that some of you really indicated those catchy areas. You didn't draw all the buildings you would meet along the road, but you are drawing those catchy buildings that even when somebody asks you the direction to your home, you would explain that, okay, when you reach this mall, turn your right or take your left. When you move towards this and you reach this point, you'll see a building of this color, turn to your right. Or when you reach this point, then you realize you're lost. Please go back, something like that, okay? So how did you use symbols, lines, and shapes? So some people use different shapes, of course, to explain the buildings and the roads and all that. Are places labeled? So we saw that in some people's sketches, they have labeled. Excuse me. They've clearly labeled the different objects that are inside their map. So thank you so much for your sketches and for the exercise. So let's move on. There's a reason why we were doing those exercises. And the next slides that we shall be having will be able to explain more. Okay, as we move, Lul, Omar, can you ask your question quickly before we move on? Omar?
No, sorry, I don't have a question, but I want to present my remarks.
Okay. Lul, we appreciate you really want to share your sketches, but like I mentioned, you're going to share your sketch in your classroom platform at a later stage. Yeah. Thank you. Okay, so let's move to the second segment of understanding the theories and techniques of GIS remote sensing and Earth observation. Now, data models. We'll start by defining what a spatial data is, and then go ahead and explain what spatial features is, so that we can tell the difference between what a spatial data is and what a spatial feature is. So spatial data refers to any data that you have, and this data must have what we call a geographic or location component to it. Okay, so let's say you have data about your office or about your school. What you need to ask yourself is, does it have any location information or component to it? Okay, location component can be in terms of latitude and longitude coordinates. It can be in terms of a street address. Let's say plot 67 industrial area. Okay, that is a location information already. Does it have a postal code? So if it has a postal code, then it already has location information. So if it has a postal code, then already it has location, or it's already geographic, or it's a spatial data already. Then, does it have an administrative boundary? If it has a administrative boundary, then it is already a spatial data. So to go ahead, spatial data can also include information about the physical features, such as elevation. I know we could be knowing what an elevation is. A terrain. Terrain is also one of the spatial data that we have. If you've ever heard of land cover data, that is already spatial data, as well as man-made features, such as buildings, roads, and infrastructure. So for example, somebody mentioned that Kampala Road, that is already a spatial data because it has some bit of descriptive location information, but also it has a coordinate information attached to it in terms of either the latitude and the longitudes, or using the eastings and the northings in other cases. Okay. Now, spatial data is represented visually on the map or in a GIS software to allow a user to analyze and manipulate the data, and further to identify patterns and relationship between different variables. If you recall the questions that we asked, question about location, question about association, question about geographical change, all these questions must be represented in the software so that they can be analyzed. Other than that, if, for example, I'm talking about Kampala Road, I'm talking about the church that Joel goes to, or the school or the workplace Joel is talking about, if I just talk about them without putting it in the GIS software, then I cannot measure the distance between Joel's home and his workplace. So I need to first put it in the GIS software so that I can be able to manipulate that information. The next thing we need to look at is the spatial features. A spatial feature refers to a specific object or an entity that is represented in a spatial data. Remember, this spatial data is something that has a geographic location attached to it. So if there is any specific object or an entity which is represented in a spatial data, it becomes a spatial feature. Okay? It becomes a spatial feature. So this spatial feature can be a point, it can be a line, it can be a polygon. So for example, we had, I think an Ibiona from Uganda represented buildings using squares or crosses. So those could be something like, I think she was trying to communicate as a point where the buildings are. We also saw some people drawing a line to indicate the roads, and then the polygon or the rectangle, the square, any shape that you drew, which is not a line and is not a point, qualifies to be a polygon. So these spatial features can be points, line, polygons that has a geographic location and can be displayed on the map or in a GIS software. So what you displayed was basically a paper map. What you drew or sketched was simply a paper map. But if you decide to use any software to draw a map, then it becomes a GIS map, or it becomes a GIS digital map. So furthermore, examples of spatial features also include buildings, just like I mentioned as the spatial objects, or rather the spatial data. It also includes the road alone itself. It could be also a lake, and it could also be a forest in this case. So all that is explained here as examples are spatial features. So remember, a spatial feature should be represented by spatial data. And when it's represented by spatial data, it must have location or geographic information attached to it. So if the data that you have in your computer does not have location information or geographic information attached to it or as part of it, then it doesn't qualify to be a spatial data. It can only qualify to be a spatial data if it has geographic or location information attached to it. And when I say geographic or location information, I mean it has to have a coordinate about it, or it could have a street address attached to it, or it could have a postal code attached to that object. So for example, if I ask you, where is the location of your office? You'll say, oh, my office is along Nyamwamba Road. Okay. Okay, for those from Kenya, you would say, my office is along Thika Road, in Westland, something like that. And it's at plot 76, maybe 9. So what you're basically trying to do is you're giving it a geographic component. You're explaining the geographic component of that object. Now, if I ask you, where is malaria? Malaria doesn't have a location information to it. But if I ask you, which people or which sub-county is being affected by malaria, then the sub-county, which is the administrative boundary, becomes a location information. But if I just say malaria, malaria doesn't have any location information attached to it. So it is not spatial data. It becomes attribute data, and attribute data of a certain sub-county in terms of the malaria infection, okay? So next, let's dive more and look at more on spatial data. So when you talk about spatial data, if you're going to represent your building, the roads and the towns, and the workplace that you live in or work in, respectively, if you want to put that in a computer, then you need to model it. Okay, you need to model it. So when you model it, then you're trying to do what we call the spatial data modeling. So let's look at this picture. This picture on the left is having a real world picture of an area. Now, if you are to represent this picture on the computer, you can represent it as it is, like this, as an image. So people will look at it as an image. But that image, you can't do a lot of things with it. You just have it for visualization purposes. But now, if you want to do analysis, for example, you want to see how deep is this water body that you're seeing here? How tall are the trees that you're seeing in an image? Then you need, if you want to do something like that, then you need to model it. You need to represent it in a geographic data. You need to convert it from the pictorial look to what we call a geographic, or to what we call a spatial data. So the process of you changing or converting this digital image or this still image or camera image into a spatial data is spatial data modeling. So in this case, in this picture, you'll be able to see that the water body here has been represented in this section here. We have also some patches and some black areas here. This could be the forest, maybe along the water body and so forth. But what is very important is that this, let's say if you're looking at this water body here, which has been modeled here, it's important to note that this water body has X and Y, and these are what? The coordinates about this water body. In addition to having the coordinates, the X and the Y, it also has attribute information. And this attribute information could be something like an area of the water body, or the type of maybe the chemical that is found in the water body. Okay, so all these components that you're seeing here is what we are talking or saying to be spatial data modeling. So what is spatial data modeling? A spatial data model can be defined as an object in a spatial database. Okay, now I'm introducing a different term, spatial database. What does the spatial database mean? So the spatial database, or the database in this case, simply means the treasurer. Remember the treasurer I talked about? When you're in a circle or you're in, let's say, a group and you collect your money, you always sit down and decide who is going to keep this money. So also in the GIS platform or a geographic information system, there is that part of the system that stores data. And that part of the system in the GIS that stores data is called a database. So why does it become a spatial database? It becomes a spatial database because it is not storing money, but this time it is storing an object that has location information. So for example, the roads have location information. The building has location information. This water body you're seeing here has location information. And the location information that it has can be seen or visualized in this table. Now, because it has location information, it becomes a spatial data. So spatial data is only stored in a spatial database. Okay? But because it's stored in the database, there, like, for example, you look at this table. These are two tables. There is the first table here, table A, and table B. Okay? Now, this table is describing the location information of this water body. But also this table is describing information about the same water body. The difference is that this table only is storing data about the location information, the X and the Y, or the latitude and the longitude. But this one is describing the characteristics information of this lake. So it's describing its area, and maybe it's also describing the type of the chemicals that are inside the lake. Now, it's very important that this table A and table B should be able to communicate or relate to each other. Okay? Now, two people in my culture is explained to be married if they are two, a man and a woman, and they are relating, they have a relationship. So the relationship there should be a reason why they're related. In this case, maybe they are married or they are wedded, okay? Now this table A and B also should be able to relate. There should be something common in table B that makes it relate with table A. So a spatial data model should have what we call a spatial data, 1. 2, it should have where it stores that data, which is a spatial database. And number 3, the database or the tables should be able to communicate or should be related. So it stores 3 things: the data, it should have a database, and information inside the database should be able to relate. So let's split this spatial data model into only a data model. What is a data model? A data model is the most recognizable level in our computer abstract of the real world. Okay, what does that mean? So we know what it means when we say spatial. Okay, we also know the data. Data, we always work with data all the time. Maybe it could be data that is describing you. But now when it becomes a model, then it becomes a representation of the actual thing. Okay? If, for example, your superior asks you to represent them in a meeting, then you become a model of the actual person. You're just an abstract or a representation of your superior. Okay? If the commissioner asks you to go and represent them, or the president asks the vice to represent them, or the minister in a function, is there as a representative, or in this case, an abstract of the actual thing. So even when you have this lake drawn here, it is not the actual lake. The actual lake is actually here, but this is a representation of the lake. And the reason why we are converting from what is actual to an abstract of what is actual is because we want to be able to manipulate it. If this lake is 1,000 kilometers from you and you want to measure the area of the lake, first of all, you cannot reach there. Even if you can reach there and you want to see the depth of the lake, it might take you some time to measure the depth of the lake. But if you have it represented or modeled in the GIS software, then you can manipulate information about it. You can go further and tell the kind of chemicals that are inside the lake, or you can even go ahead and measure the area of this lake without actually being in the lake itself. Now, another component that is very important when you're looking at spatial data modeling is structure. Okay. The structure is how we organize the information in the computer. So, for example, in this table A and B, we decided that, okay, for this table, we want location information to be organized in table B, and then the attribute information should be organized in table A. Now, the importance of this is that in case some changes is made to this table, you don't have to reorganize this table A. Okay, you can just edit only table B, and then automatically the information get linked because there's a relationship between the two tables. So this is a very simple example, but if you have a very large database, let's say you've done census for the whole country and you have millions of records in your database. Now, just imagine changing one component of it. You will have to change all the rows of that component. Now, if you do things like that, people will call you disorganized. You're not organized because things are messed up. When you have to change something small, then the whole system has to, first of all, not even to work or not even be able to display for some reason because you're making changes. But if you structure your data very well inside a database, then you can be able to change any part of the database without affecting the other tables easily. So data structure is how we organize the information inside the computer. There's also something called binary. Binary is a machine code, and it helps us to know, or it is how we record that information inside the computer. Now, this is not something that you should be worried about because the way the computer is working is none of your business. What you want is, first of all, can the computer do for me A and B? Two, is what the computer doing right? But in actual sense, when you draw an abstract of this data of the lake into the computer software, what the computer is seeing are these numbers. So these are binaries. It only sees 101010. Doesn't see your object the way you see it. Okay, that is what you need to know, that inside the computer, the way it is doing things is very different from the way you're seeing them. Okay, so let's dive into what are these data models. There are a number of them. So a spatial data model is a framework for representing and storing spatial data in a structured way. So now we have combined three things: spatial data, a model, and structure. So that is what makes a spatial data model. First, it's a framework for representing and storing a spatial data, but not just storing. It has to be stored in a structured way. And this is because it will allow one to efficiently process and analyze, as well as visualize the data. So if everything is well structured, if everything is stored, if everything has been processed very well using the right framework, then somebody can efficiently process that data, analyze it, but also be able to visualize it. Okay? Let's say you have data about the lakes, and then you have data about the rivers. Now, if you mix the rivers with the lake data, what if you want to measure, what if you're doing analysis and the rivers disappeared? Okay? That means when you're doing the editing of the rivers, then you have to also edit the lakes. So the lakes will be affected just because you're editing the rivers. But if for some reason you decided to separate them, you say the data for the river is structured alone, and then the data for the lake is structured alone, the data for population is structured alone, then you can efficiently process this, because when you're processing it, you're only processing individual structured data and not mixing things up. Now, quickly, the common ones that we use in terms of this spatial data model, one is a vector data model. So this model represents the spatial features. Now you remember what a spatial feature is, as points, line, and polygons with X, Y coordinates and topological relationships. Now, I talked about relationships. In the GIS, the relationship we are talking about is called topological relationships. We are going to talk more about this in the next segments of our lecture. So the vector data model is commonly used for mapping and analyzing discrete objects. So mark this point, discrete objects. So discrete objects are objects that have a clear boundary between one object to the other. Okay? How can I explain that? When you see the boundary between a lake and the land or the shores, there is a clear boundary. There is water this side and there is soil or land on the other end. Okay? Now, it becomes discrete because there's that clear boundary. So anything or any object or any earth feature which has a clear boundary between them can be best, and mark those words, can be best represented as vector data model. The second one is a raster data model. So this is a model that represents spatial data as a grid of cells, whereby each cell represents a specific area. Okay? Each cell. So let's say you have a grid of cells. Okay, I'm going to just make a quick grid of cells here. So what I mean by a cell is this single unit. Okay, sometimes people call it pixel. So each of these cells, so we have 1, 2, 3, 4, and 5 cells. Okay, so these cells are what can be represented as a raster data model. And then this raster data model should represent a specific area and should contain a value. So it doesn't just stop at having these grids, but it should represent a specific area and should have a value. In this case, I'll put 1, 2, 3, 4, 5. So this would be a value for each of these cells that you're seeing here. So how do we use that in GIS? So objects or components that include elevation, temperature, and rainfall are best modeled in a GIS software or a GIS system as raster data models. Okay. Now, the reason why it is like that is because there's continuity. There is continuity between each part of the object to the other. So let's talk about elevation. Elevation looks like, look at the slope of an area. Unless in any occasion, like in the Rift Valleys, you might see a clear difference between one part of the slope and the other. But normally, slopes are continuous. So you start climbing a hill slowly, slowly as you move to the top. It's not like it's low, a low part of the slope and a high part of the slope just at once, nothing like that. So there's a continuity between the low part of the slope and the high. Look at temperature, okay? You can't have cold freezing temperature next to boiling temperature next to each other. You can't have that. They can't exist. You can't have ice next to fire, for example, okay? So if you're to have ice and fire, there should be a continuous coldness as the temperature keeps increasing to the highest. Okay, so there's continuity between the extremes of temperature data, even rainfall. If it rains in your place highly, I don't know, for some who have driven on a rainy day, you'll find that when you're going to, you'll move from a clear area. As you're driving towards where it is raining, you'll first encounter drizzles. Then after encountering drizzles, now you start entering and getting droplets of, large droplets of rain. And then the whole, when you enter inside where it is raining, then you have a full downpour of rain. Another special data model is called the network data model. So this data model represents spatial features as a series of interconnected nodes and edges. So things like the road networks, the transport networks, the roads that you use, these are all network data models. For example, in our abstract or the mental map that we were drawing, what we were actually doing was modeling, because you'll see that the roads were interconnected at the junctions and the roundabouts. And this kind of interconnectivity is the network modeling of the actual roads in the ground. The last part is what we call object-oriented data model. Now, this is unique from all the three in that, and most of us, when we were making our drawings, we were using object-oriented data model. So what is a building? We were showing it as a building, and the roads as a road. So this model represents a spatial data as a set of objects. So the building, the church, the school, the Sorry, we had some bit of power side here. Just get back. Yeah, we lost us because we had a power issue, but we're back now. Okay, so finally, object-oriented data model. This is a model that represents spatial data as a set of objects with the properties and behaviors. Now there's something new here, behaviors. So we have the objects that we have been talking about. The object could be a building. It has properties, okay? The roof type, the wall is made of maybe wood, or it is made of bricks, or it's made of soil. But also there's another part of it, the behavior. So it captures three things: the objects, which must have a spatial or geographic component on it, its properties, which sits in the attribute table, and then the behaviors of that object. So this is commonly used for complex spatial applications such as the three-dimensional modeling and assimilation or simulation that is used in GIS. So the gentleman who asked about artificial intelligence and machine learning, these are components that come into play when you're using these two important data applications. So finally, spatial data models are important for effective management and analysis of spatial data, and they help ensure that consistency and interoperability across different systems and applications. What this interoperability is saying is that if I make a shapefile from Uganda and I send it to Mauritius, or I send it to Ethiopia, and then the gentleman in Ethiopia opens this same shapefile, it should be able to display the same location, the same information about what I've shared, okay? And then the person in Ethiopia, if I make this software using QGIS, and then the person in Ethiopia is using ArcGIS, the data that the shapefile that I've shared should be able to open in any of the softwares. So interoperability is ability for different systems to communicate with each other effectively without any barrier, okay? So for any spatial data that you want to model, if, for example, you model the roads and you put them as polygons and you send it to me and you say, these are roads, I'll probably start thinking, no, roads have never become polygons. Roads have never become squares. Squares represent buildings. Now, if you're giving me roads and they are in squares or they're in dots, so let's say a road is linear, and then you send me a road using a dot or a point, and you say, this is which road? Let's say Kamukama Road, okay? Kamukama Road. And I'll ask myself, but roads have never been points. It doesn't make sense. If I send these roads, which are points, to a computer, and then I force the computer to say these are roads, the computer is going to reject because the interoperability component is not well captured. Unless we decide to say, you know what, from now on, roads are points, okay? So the person in Ethiopia will also agree that the roads are points because that's what we have agreed on finally. So continuing, the spatial objects can be represented in object, which is the vector mode, or raster, which is the image mode. So when you look at these two pictures, one is a raster and one is a vector. So the one on the right is a vector and the one on the left is a raster. Enoch? Enoch,
Yes.
your hands are up.
Sir, you talked about that you cannot represent roads as dots. So what if I use lines that are in form of dots, like a dashed line to represent road? Am I wrong, or it is totally has to be a line, like a line, a continuous line? Thank you.
It's good you've said a dashed line. So you've already said a dashed line. Now, normally at different scale, a road can be seen as a polygon, but in actual sense, it is not a polygon. It's because of the width of the road that is making it look like a polygon, but it's not a polygon. It's a line. So the line can be thick or it can be thin. Okay. But in actual sense, a road is a line. It's not a polygon and it cannot be a point. Okay, Enoch, I hope I've responded to you. In case you're not satisfied, please let me know.
Thank you very much.
Okay. All right, so spatial objects can be represented as an object, which is a vector, and then raster, which is an image. So in object mode, which is vector, individual spatial objects can be defined as points, lines, and polygons. I'm still echoing the same thing. And then also the image mode, which is a raster, individual spatial objects can be defined as a set of continuous cells, which are known as regions. We'll explain that in details. Now, although the spatial objects and phenomenon can be defined in object and image mode, discrete spatial objects can be more accurately represented in object mode, and continuous phenomenon of spatial objects are meaningfully represented in object image mode. So this statement is just saying the same thing that we said earlier, that discrete spatial objects are vectors, okay? These are vectors. And then continuous phenomenons are rasters, okay? So for example, here we have a vector and an image. Now, this image is a raster image. If you zoom in, you'll be able to see the continuity between the colors that you're seeing. But also, things that are discrete can be represented in an image, okay? Doesn't mean that things that are discrete cannot be represented in an image. They can still be represented in an image. But the best way to manipulate, to analyze them, is to convert them from a continuous image to a discrete image. So this is discrete, and this is continuous. Okay. Now, continuity and discrete doesn't mean that a lake, for example, cannot be shown as a continuous object. It can be, but it will not be accurate. If I tell you right now to measure an area of this lake from this image, you might get an area, but it won't be that accurate. But if you convert it into a vector, then the accurate area can be attained in terms of the measurements. So going further into vector data models. So a vector data model is closely linked with discrete object view. That's what I've just said. And in a vector data model, geographic phenomena are represented in 3 different forms: points, lines, and polygons. Now, we have looked at this part in depth. Let's focus ourselves on this image. So we have the points. So points, there is 1, 2, 3, 4, and 5 points. Now the attribute table, okay, which is the descriptive information of these points, is also located on the right. So you'll see that 1, which is this point, the tower name is that, the height is that, and the format that. And point 5 is here. The tower name is BBC. The height is 212.1, and the format is news. So what we're saying is that even if you have a geographic information, in this case, a geographic vector data model or the spatial data model, it must be accompanied by the attribute information about it. And this applies to this. Now, for the lines get a little bit different. The lines in this case, the information is about the segment of the line. So this segment here is segment 8, and this is the attribute information for that segment. For the polygons, which could represent the buildings, it also has attribute information attached to it. But we shall look at how the coordinates for the polygons differ from the coordinates of the line and differ from the coordinates of a point. Okay? Literally, a line is generated from linking 2 points, and then the polygon is generated by linking more than 2 points and closing it back. Okay? For the lines, they don't close normally. They join, but they don't close. Okay? We'll see that in details as we move forward. Going ahead, vector data model often contains vector topology. Okay? Now I talked about topology, and we are going to look at it in details at this point. So, what is a vector topology? Okay. Topology, which is going to explain later, but a vector data contains a topology and enforcing strict connectivity and recording adjacency and planarity. So let's look at this in details. What am I trying to mean when I say this statement, that vector data often contain vector topology, enforcing strict connectivity and recording adjacency and planarity? So early systems employed what we call the spaghetti data model of vector. So in this case, you have lines that are moving from right to left, up to down, maybe east to west and all that. But these points, these lines are not connecting, okay? Yes, you might see that at this point, this line and this one is connecting, but there's no connectivity between the two, okay? If I decide to move this part of the line down, it will just stretch, but it won't, it will just break. Probably it will be this one that will move and this one will remain. if I decide to move this line, this side down, okay, this line here is not going to move. It will remain there, and it will be only this line that will stretch. So that is a spaghetti way of representing features. So in early systems employed this type of data model in which lines may not intersect when they should and may overlap without connecting. So in this case, there's an overlap here between these 2 points, and there's no connectivity. Now, this part of the line, this one and this one, are supposed to connect just like this other part. But as you can see, there are 3 endpoints instead of 1 endpoint here. Now, the spaghetti model severely limits spatial data analysis, and it's little used except for very basic data entry or transition. So because there is no connectivity between these 3 points, then analyzing this data becomes a problem. But if they're connected, and I'll show you later, then analysis becomes more useful. So look at spaghetti in terms of the pasta that you cook at home, okay? So they're just straight lines or strands that are not connected with each other. So the topological model this time creates an intersection and places a node at each line crossing, recording connectivity, adjacency, and maintaining information on the relationship between and amongst the points, lines, and polygons in spatial data. So in other words, topological data model of vector is an opposite of spaghetti data model, because first, it creates an intersection between the lines. It places a node of each line crossing. So for example, we have this, there's 1 node, 2, and 3. In this case, that's in topological relationship, you only have 1, okay? Also, there are 2 lines crossing each other here. Now it has created a node which allows them to link at this point other than this one, yeah, okay? Adjacency and all that gets to play or get to be introduced when now you're introducing topological data model. So this greatly improves the speed, accuracy, and the utility of many spatial data operations. Okay. Now let's look at how topology really works. So first you have your first polygon, and we're going to use polygon to explain this in details. You have your first polygon right there. And then you have the second polygon that is right there. So you have polygon 1, which is in green, and you have polygon 2, which is in blue. Now, you'll create a vertex on polygon 1. So we are first considering green. So the vertex is the point on the corner of a polygon. And then when you create the first vertex, another vertex is that one, 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 and then another one is there, and you have the last one there. Mariam, kindly put on your mic and ask your question. Mariam, we can't hear you. Your hand is up. Mariam, come again. I'm having a problem with my mic. I need to check my system. I can't hear anything.
We are getting you, Thomas.
Okay, Mariam, go ahead. Now I can hear you.
I think she's not talking.
Come again.
Maybe she raises
Okay,
the hand.
maybe Mariam, you'll try asking this question later when I can hear you.
I request that we move on. Maybe she can ask later.
Sure. Yes, Kato. Thanks. Okay, so we have clear this. So we have polygon 1, which is in green, and then we have polygon 2, which is in blue. The vertex or the vertices in this polygon are along the corners, okay, along the corners of the polygon. Now, as you've seen, those are the vertices for polygon 1. Now, when we go ahead, we shall now create the vertices for polygon 2. Remember, what we're trying to do is to say the relationship between polygon 1 and polygon 2 should be enforced. Okay, we don't want to have polygon 1 having its own boundary and polygon 2 having its own boundary. The problem is that when polygon 2 reduces, polygon 1 will not increase. When polygon 2 decreases, polygon 1 is not going to reduce or increase. So we want to make sure that when polygon 1 reduces in size, automatically polygon 2 should increase in size. Okay? But if they are not interlinked, if they are not together, then there will be no relationship between polygon 1 and polygon 2. So let's go ahead and see the vertices for polygon 2. So it's that one, that one, that one, that one. Now what you're seeing moving in red is the boundary that is joining the vertices for polygon 1. So what is interesting is that when two polygons are neighboring each other and the boundary between each of them is constrained, the red line cannot close out. It moves from the starting point and it closes, but not complete closing, because there is a shared boundary in between here. So this red line was supposed to move and then close to here to show that it's a boundary for polygon 1. But because there's a shared boundary between polygon 1 and 2 at this point, the boundary for polygon 1 stops at that point. And then I'm going to add the boundary, which we call the arc, for polygon 2. So for polygon 2 also, it will not close up to this point. It will just move and stop at this point because there's a shared boundary here. So then we have arc 3. Arc 3 is now the polygon, or rather the line of the boundary between polygon 1 and polygon 2. So quickly, you'll be able to see that we have 3 arcs. We have arc 1 for polygon 1. We have arc 2 for polygon 2. And then where there's a shared boundary, it makes arc number 3. So between arc number 3 and arc number, between the start and the end of arc 3 is what we call the nodes. So in this case, these are not vertices. These are not vertices. If these polygons are supposed to be together, then this becomes a node. And because there are 2 polygons that are together. Now, in a database, this information has to be structured. And for it to be structured in a proper way, each of the information that we saw 1, we saw polygon. So the polygons are green and blue. The second component is the vertices. So we had the vertices for polygon 1 and then vertices for polygon 2. So that's the second component. The third component is the arcs. So the arcs is the line moving along the boundary for polygon 1. We also have the arc for polygon number 2. And then the third one between polygon 1 and polygon 2. And then the last component is the nodes. So the nodes now talks about the point that is common. Rather, it's common for both polygon 1 and polygon 2, but do not share the boundary. So, for example, you see this is not a node, okay? It's not a node, but rather it is a vertex that is being shared by this and that. So in GIS, this has to be well structured in such a way that you have a table which stores information about the arcs alone. Then you'll have a table that stores information about the nodes alone, okay? So that if you have, let's say, the arc topology now will combine the different aspects together. It will combine the arcs and the node information together. So for example, in here, in the arc topology, we have the arcs, which is 1, 2, 3. We know what they are. And then it's going to say a start and the end node. So the start node is N1, this one. And then the end node is N2, is this one, okay? So for arc 1, you remember what arcs are the boundaries, okay? It has the start node, which is this one, and the end node, which is this one. For arc number 2, the start node is this one. It moves like this up to the end node, which is 2. But for arc number 3, it has N2, which is the starting point, and N1. So it's opposite of the other. And then it will talk about the polygons, which one is on the left and which one is on the right. What is very important is that we are seeing there's another polygon called E. So polygon E is not necessarily colored, but anything outside polygon 1 and 2 becomes E. So it's just an imaginary polygon outside. So this is the arc topology. But there's also what we call the arc coordinate data. Now, in the GIS software, you normally don't see this. You don't actually worry about it because the software is doing everything for you. You're not bothered, you're not aware that it's actually doing this. But theoretically, you need to understand how the relationship is working, because you need, as a component of GIS, you need to appreciate and also know whether the data that you're obtaining is actually accurate. If it is not accurate, then you're giving somebody a wrong analysis. You're reporting something that is wrong. This might not be very, this might not be very dangerous if you're working on a small project. Philemon and Abdi, you're going to talk shortly. Let me first finish explaining this, then I'll call you up. So keep your hands up. So if you are working for, you're predicting maybe a landslide using a GIS, and then you just make a mistake, okay? You run an analysis which is wrong, and then landslide occurs and millions, hundreds of thousands of people die just because your simulation or analysis that you've done was wrong. Then it becomes very dangerous. But if you're just maybe talking about the crop yield, or you're looking at, you're mapping the crop area, and you make a mistake by maybe 1 or 2 area hectares, maybe wrong, it may not have a very big impact, but you need to know that as a GIS component, your role is very big to check and make sure that what the computer is giving you is the right thing. If the computer is giving you something wrong, in land use land cover classification, there's what we call the error matrix. There's something we call the accuracy assessment. The computer definitely has done the work, but you need to validate this work that the computer has done. So let me start with the Philemon. Philemon, your hands was up earlier. Then Abdi is going to come next.
Hello, good morning.
Yeah.
Hello?
Yes, I can hear you.
I am Philemon calling from University of Jos, Nigeria. I just want a clarification concerning the nodes. That you said the nodes are the connecting point between 2 features, right? Hello?
Yeah, 3
Hello?
arcs.
Can you hear me?
Between the arcs. Yes, I can hear you.
Yeah, between 2 features. So I'm just thinking, what if we have a line that intersects the polygon? Is the point that the line intersects be considered as a node also?
The point that intersects, yes, because the line is an arc already itself, and then the polygon will have also its arc. So it becomes a node, yes.
All right, thank you very much.
You're welcome.
Yeah.
Next, Abdi.
Yeah, hello, can you hear me?
Yes, we can hear you.
Yeah, so I think it's very quick. I want to ask you, is the start for the arc 3 and not N1 as the other 2 arcs? Because as we can visualize it on the polygons, it's, I think, like, I don't understand why N start of the arc 3, the third arc. Thank you.
So Abdi, this is basically in terms of how you've digitized the direction you've decided to take. So alternatively, N1 could also be the start if you've decided to digitize from up to down. But because if you look at the years, so it depends on the direction that you've decided to follow. And this is very, very important when you're digitizing roads, okay? When you're digitizing roads, you need to be very, very careful the direction of the roads. Now, for the roads, it may not play a very dangerous role, but let's say you're doing a watershed analysis and then you decide to give a wrong streamline direction, the direction of the streams to be wrong. Let's say the streams are supposed to move from the minor streams to the major stream. Now, if you decide to digitize it the other way around, then your analysis becomes very wrong, because you're saying now the water is moving from the lower part of the slope towards the higher part of the slope, which is very wrong. So when you're doing such kind of digitization manually, then you must be conscious of the direction you're following. But in this example, N1 could also be the start of Arc3.
Okay. Thank you.
You're welcome. Thank you. So we continue. Now, more slides on topology. There are more slides on topology because it's a subject for people to understand. So I put more slides for it so that we can, if you have not understood it in one slide, maybe in the second slide, you might understand. Now, we have our features, and in this case, we have the features which are points. So we have point Q, R, T, and S. Now, representing that in an attribute table, you'll have, let's say you're creating an Excel which is an attribute table for these points. So you'll create the first column will be point ID, which records information on Q, R, and T, and S. Then next, you're going to have the X and Y columns, which is capturing the coordinates. So this is the X coordinate values, and this is the Y coordinate values, okay? You could also have more columns, maybe talking about the point. Maybe this point means a highly polluted area, or it could mean maybe a particular depth of the well. Maybe it could be this well is maybe 100 meters deep. This one is 50 meters deep, and so forth. Okay, so that would be more of those attribute tables that you're having. Now, next, what you're going to see here is that for the lines, the table becomes a little bit more complex. First of all, you have the points, individual points, okay? And then these individual points, to make a line, has to be joined. So for example, if it was this one, you'd have to join this point to this point to make one line, point that point to that point to make another line, and then that point to that point to make that line, okay? For the line, you would stop there. But to make a polygon, you'd have to continue and then close it. So that's what converts a point to a line and then to a polygon. If the lines have closed back to the starting point, then it becomes a polygon. Now, in terms of topology, how the computer structures this inside. For the lines, it's going to create an attribute table which has the line ID. So the line ID is saying this line from 1 to 4 is line 11. So as you can see here, it's line 11. The beginning node is 1, okay? The end node is 4, okay? For line 12, the beginning node is 4 and the end node is 2. For line 552, the beginning node is 2 and the end is 3. Remember, it can also be the other way around, depending on the direction you have decided to follow. In my case, I'm saying I'm moving from 1 to 4 to 2 to 3. Somebody might be moving from 3 to 2, to 4, to 1. So when you're doing a digitization, the computer is recording this information that, okay, this person has moved from this to that to that. If another person has done it the other way around, the computer will also record that information that you've moved from this to that to that. And that is when you're doing analysis, for example, you want to say, Google, what is the distance from where I am or from my home to my workplace? So what Google is going to do, it's going to say, okay, so your home is the starting node, and then your end node is your workplace. So that's the direction it's going to follow. But also you can decide to say, okay, from my workplace to home, okay? You can also decide to say, to tell Google that, no, the starting point is my work, not my home. So Google will also do the calculation for you, because traffic, if your case is to define traffic, traffic varies with time and direction of movement. You might find that traffic from your work to your home is 2 hours, but from your home to your work is less than 30 minutes. And the reason is because of the effect of the direction of movement, in this case for the traffic during the day. Abdi, you have a question?
No, I think I haven't deleted my raised hand before, sorry.
Okay. All right. So next is we're trying to look at the topology and how the features link up with what we call the topological tables. So that's what I didn't mention, is that when a file is being created, when you're doing that digitization, what the computer is doing, it's also creating a topological table. So the topological table is the one that stores information about the relationship between the features that you are digitizing at that time. Okay. So here it's now saying, okay, next is we have finished with beginning node and end node. So the next one is the left polygon and the right polygon. Okay. So this may not make a lot of sense when you are stopping on lines. When you're stopping on lines, it normally stops here, or rather, sorry, here, going back. But now, in this case, it's trying to say, okay, what if you have a polygon, okay? So it will ask that what is in the left and what is in the right. And we can see more details of that here. So this table is a continuity of this one. So for this case, if these lines have been joined and they have become a polygon, you'll have the polygon A and polygon B. So furthermore, in the topology for the topological table of a polygon will have a little bit different structure. So it will have the polygon ID, which is A and B. And then for the lines, it will just going to consider them as a series of numbers. So for example, for A, polygon A has line 11, 12, 52, 53, and 54. For polygon B, it is going to have 52, 13, 14. Okay, it's following this other way around. So it's going to have 52, 53, 19, 15, 14, and 13. Okay, so depending on how you've digitized the polygon and so forth, the direction is going to be stored in the topological table. And this topological table is the one that is storing the relationship between those two polygons. Now, if you've ever done digitization, at one point. For those who have tested it, maybe. If you create 2 polygons, I'm just going to create one here. So if I create this polygon, okay, and then I want to add another polygon, okay, I could do like this. I could start like that and create another polygon. But in actual sense, this polygon and this one, the neighbor between them is actually the same. But because I digitized 2 of them, because I started from here, then went here like this and closed, now I'm having a funny gap between polygon A and polygon B. Now, what if I draw the first polygon and then I say, you know what, for the second polygon, I want the node to be the same. So instead of drawing a line here in the middle, I just draw, just draw like this, and I stop here. I don't go in here again. I just stop here and I say, this should have a shared node. Okay, there's a node here and there's a node here, so they are shared. So then this polygon then becomes a topological structured, a well-structured topological vector data that we are having. So the statement here is basically saying that an example of vector features and corresponding topological tables. So information on the adjacency, okay, this polygon is adjacent to this one, okay. Connectivity, it's connected by the same node, and the other spatial relationship may be stored in a topological table like I mentioned earlier, and joined to features by indices. So the computer basically tries to do this for you, but you need to know that because, for example, if I send you data which has a topological table, and then for you say, okay, this extra table is very idle, it's redundant, let me delete it. So the moment you delete it, this automatically, this polygon A and B will not be adjacent to each other, but they will separate automatically because you've deleted the relationship table between that. And that's why we are trying to understand the issues of the topological tables. Now, index or indices is what a computer tries to store based on the different features that you have. So the computer stores an index or an indices so that it can be able to remember based on the index that you've stored with the data. So the index is basically about being able to remember, but to also retrieval. So when you need to retrieve an information from that table or from one feature, then what is indexed to it also will be retrieved. In this case, the topological relationship. Okay, so topological consistency relationship. So just run a few things here. Okay. So first, every line is bounded by 2 points, those ones. So there's a start point and the end point. Next, for every line, there are 2 adjacent areas. What it's meaning, or what I mean here is that there's this area on the upper side and there's this area B, okay? Now next, so I mentioned the area on the left and that on the right. And this would be more like a polygon in this case. Then every area or polygon is bounded by a closed circle of points and lines. You've seen that. Now, every point is surrounded by an enclosed circle of a line and areas. So what you're saying is three things. Last time we had only 2 nodes. Now, because we have 3 polygons, we have 4 nodes. We have the node, this one, this node, and this one. Now, this node is because of the adjacency, or it's because of the link between this polygon in blue with green. The node, this node is because of the blue polygon and yellow. This node is because of the intersection between polygon green, polygon blue, and polygon yellow. This node is because of intersection between polygon green and polygon yellow. Okay. So like, I don't remember, somebody asked this. So lines intersect only in points. So now we want to look at spatial relationship. So we talked about adjacency, but there's more to adjacency in terms of relationship. So these spatial relationships are both topological enforced and non-topological enforced. So one, there is a disjoint. 2, there's a meet. So if 2 objects meet together and they're not actually sharing the boundary, but they meet one on top of the other, then that becomes a meet, not what you will see later. So if they're equal, then one polygon is just on top of the other. Another relationship is inside. So inside is when one polygon is inside another polygon. There's a difference between the covered by and inside. So if, for example, you'll be able to see that this inside and covered might look the same, but not necessarily. So this polygon might be inside, but as you can see, the area between these parts to this section is not the same. This one, on all sides, the area or the distance between the boundary of the inside polygon is the same in all directions. For this case, it is not. This one is just inside. Covered by is on top of the other. Another one is contain. So contain is also different from inside. Inside one, the polygon in red is on top of polygon the blue polygon. In this case, it's a reverse. The other one is on top and the other one is on the bottom. Another is covers. So it's just covering this. And as you can see, it almost wants to look like inside, but the difference is that the inside polygon is touching the boundary on the inner side. For this case, the meet, it is touching on the outer end. An overlap, you can just see that there's an overlap between the 2 polygons. Okay, we were supposed to go through the raster data models, but it's already 1 p.m. Yeah, it's already 1 p.m. So that means it's already time. So I want to maybe ask Doctor to chip in, but the next session will be to enroll you to the platform so that you can be able to access the materials that we are using for the training.
Thank you, Thomas. I'm really happy that you've been able to go through that that content, quite a lot of materials, but being able to introduce our colleagues to the GIS. I know it is it may not be that to comprehend it very fast, but we are here to support you to ensure that you succeed. And also, like we said, this is introductory. Indeed, a number of these concepts, once you pay attention, you should be able to pick them. So thank you again, Thomas and Juliet, for taking us through that. Now, I'm wondering, Thomas, because in terms of time, we already passed time. Are you taking them through the enrollment now, or we want to do it such that, do they have to self-enroll?
Yeah, I wanted to share the code and then they can be able to enroll.
And access the materials. Then whatever is not covered, we can be able to start with that tomorrow, not so?
Yes.
So that is something that is okay. But I also wish to mention that the number of people who are joining in, can we pay some attention, please? The number of people who are joining the class, and the reality is that a number of them are not registered. So I'll request Juliet to share the link for the online registration. For those, we should just put this for those who are joining now, such that we can have them. We can have them as part of this class. Can we please pay attention? Can those who are speaking mute their microphones, and then we wind up this session in a short while, please? Thank you. So what I'm saying, that Juliet should be able to share the link for online registration, such that all of those who are joining in can be able to register. And then we have them registered on the system, but also don't forget to register in Zoom, because we shall use Zoom as the basis for, we follow up who is participating in the trainings. So make sure you also register here. Thanks so much, Thomas. I think now you can take them through, and after that, you can close this session. I'm happy. At what time are we starting tomorrow?
Tomorrow
Thomas,
we are starting at exactly 9.
9 or 9? I think 9 will be okay. We shall be able to do the recap and then get into the materials for tomorrow. So you'll be there at 9, and then we go through these materials as fast as possible, such that we can be able to accomplish what we have. Thank you very much, and see you tomorrow. I'll be just listening in, unless when there is something critical, that's when I'll come back. But have a nice day. Let Thomas take you through the enrollment. Thank you.
I'm wondering, so I'm going to put the link and then see how many people do not have access to the course. So that's the link. I've just put the link in the chat. When you in the link, just try and confirm that when you log in, you should be able to, under my courses, you should be able to see the course right here.
We can't hear you.
Okay, but John, I don't know what you mean that your login details. There are a number of people who have accessed the site that I shared yesterday. So I don't know what you mean.
Thomas, I may come in. Huh?
Yeah.
I'm Paulino from ICPAC. Actually, it's not an issue of link. When you click on that link, you will find yourself inside the learning portal. Then it will ask you to log in using a username and password. Now, when we were registering that day, we was just popping information like a name, email, and phone, and something like this one. So now the issue is where everyone can get the username, where now the username and the password. Because when you log also as a guest, it will tell you as a guest, you are not allowed to access this material. So the login is the one is a main problem I think most of us are facing.
So yesterday when I sent an email, did you receive an email?
Yes,
yesterday?
I received an email. Yes, I received that email. Then I click on the link down there because in that email you was asking to register. So once we receive email from you, mean already the email we receive based on the registration we did before. Therefore, we're able to get email from you. Now, is that registration from the beginning is the one supposed to be used as a login? Because now I may share my screen for me to be clear on what I'm talking about, by the way.
Okay, let me stop sharing and then you share.
I think I'm not allowed to share. Someone.
No, I've activated. You can share.
Okay. I think you're able to see my screen for now.
Yeah.
Yeah. So like this one now, will ask me up here to put my name because like yours now you have a Thomas there. So where I will get the username and the password because already I received this email. I'm able to open this one using the link.
First read your email because I created username for everybody. So you might have to check your email.
The one you sent yesterday.
Yes, you may open it for everyone to see, or if you're not comfortable, you can keep it away and then.
No problem.
Okay. So can I look at the email that you received from me yesterday?
Okay.
That is, scroll down.
This is the one. Yeah.
Yeah, just go up a bit.
Yeah, now you're asking to create a new, this one, now, not here. So where
because scroll down. Just scroll down a bit, I see something.
Yeah, now I click on this one, will let you to that main page. But that main page also will still ask you about the login again.
Okay, let it open because what I had done is to allow you go into the system, and then when you go to the system, you are supposed to change the password. Like it's going to allow you in.
Information missing, huh? Maybe some of us didn't receive, maybe through another communication. Because even yesterday, I spent a lot of time on this one. Now where I will create the new password because I suppose, even I try to click on link here down, on this link, when you click on it, it will open that platform. Then the platform will ask you also the password and username, for example.
Okay, I get it, Paulino. What I'm going to do is I'm going to, so based on the Zoom today, I'm going to generate the whole list of the attendance and then send them the credentials for logging in.
Very good, very good.
Okay.
I have a comment,
Much
sir.
appreciate.
Yes, Ali.
Yeah, sir, I have a comment. I was facing the same challenge previous, but what I did, I was clicking the link that he showed to tell me to forget email was over here. Then once I click that link, it opened me another email link so that I will change my password. And where I get my username and password. So maybe they can do that easily.
Were you able to change your password?
Yes, I was. I think they can do that. They can click the link that it will forget password. Then they go to email and they click sending link and they create a new password. Over there, they receive their username. That is what I did, and now I managed to join.
Oh, okay. Yeah,
Yes.
because I even created a username and everything for people. So basically, it was supposed to allow you to get into the system, and then after getting into the system, but nonetheless, please simply put your email on the chat for those who have, if you have not sent, but if you have sent already, please just put your email on the chat. We'll generate a new list of participants again for today, and then by the end of this evening, you'll receive an email asking you to log in, and then you change your password, and then everything should be okay. You'll forgive us. Day one is always a bit like this, but as we move on, things will normalize and all will be well. So kindly, if you feel you have not been registered in the platform, simply put your email address here. Juliet is going to compile all of them for me, and then I'll upload. I'll send you the login details so that you can easily log in without any problem.
Thank you.
You're welcome. Joel.
Yes, sir. I'm having the same issue with sorry, based on his comment, the last person I just commented, I also tried changing my password, forgot password, but it was telling me invalid email. So I think that did not work for me. Based on what he did not really actually work for me. So I wanted to just make comment on that.
Okay. But remember, the email that you should use is the one that you have received the link on.
Yes, that is the one I used.
Okay, no worries. Just put your email address there, and then we'll be able to compile it. All right. Okay, otherwise, see you tomorrow. For those who could not make it today, let them try to endeavor to make it tomorrow. In case you know a friend who couldn't make it today, just remind them that tomorrow will be if they attend tomorrow, then they will have acquired the 80% of attendance and the following days. But if they don't attend tomorrow, then they'll probably wait for another platform, another opportunity when we send out a call again. So thank you, and wish you a good afternoon. Kindly put your email address if you have not received the link for the training.
Good afternoon, and tomorrow then.
The email address.
Thank you. Then I can do you.
Thank you, Thomas. Bye.
All right, bye. Okay.
Thank you. See you.
All right, see you guys. See you tomorrow. Thank you, Janine.
Thank you.
All right. Asma, thank you.
Good afternoon. Thank you.
All right. Good
Thank
afternoon.
you very much, sir.
All right. I hope you've
Thank
learned
you.
today. Samia, Mando, good to
Samia
see you.
everyone.
Good to see you. Yeah. Amna Sulaiman. Okay. Saul, good to see you. George, Alex.
Thank you.
Manal, yes, Manal, good to see you. I see the whole group. Greetings from Juliet. I hope you were in Nairobi. Okay, Samson, good to see you. Ibrahim, Abdallah, salam alaikum. Salam alaikum, Alamain, Asma. All right, Evelyn, good to see you. Kamukama. All right.
Good afternoon. Thank you. See you.
Yes. Okay, Israel, see you too.
Thomas, I have just one comment.
Yes, please.
Okay, accessing the e-learning platform may be challenging if all of us try to bombard the server at once. I'm getting some challenges trying to access it actually. The server is timing out.
Okay.
So maybe if you can just access it in classes or groups, not all at the same time.
Okay.
It's just a point.
All right. Okay. Morris is IT person, tech is guru. So thank you, Morris, for those tips. We'll try and fix some. Actually, you'll come and help me fix some of those issues. I'll request you for your expertise. Thank you. All right. Thank you so much and wish you all a good afternoon. Bye.